This is part 2 of 1.03 for core gas laws. All right, so we're talking about Charles' law, talking about gas volume and temperature. And let's go ahead and take a look at our cylinder here. So K stands for what? Kelvin. And so this is our temperature. So 293.4 Kelvin is our temperature. And again, there's no markings on the cylinder, so we have to assume that that is the correct volume. Let's explore the relationship between temperature and volume. This cylinder has a movable piston, which is this part, that contains a fixed amount, same amount, of gas molecules inside at room temperature. The current pressure and temperature is recorded on the chart. And that is wrong, because it's not the current pressure, it's the current volume, because the pressure does what? It stays the same. As we increase the height, the volume of the gas increases in proportion with the temperature. Why? Because the warmer the molecules get, are they moving faster or slower? Faster. So they're going to move faster, they're going to spread out. And of course, as it gets even hotter, it's going to take up more space. And so we have our positive trend or best fit line here showing that as the temperature goes up, so does the volume. If you heat the cylinder, the gas molecules receive more energy. They move faster and collide against the walls with more force. As they do, the space between the molecules becomes larger and the volume of the gas increases. In contrast, if you cool the cylinder, the gas molecules lose energy. They move more slowly and collide against the walls with less force. So they're going to be closer together, less volume. The distance between the gas molecules gets smaller, and so does the gas volume. So let's look at this one mathematically. And again, we have our graph. As the temperature increases, so does the volume. And so what do we call that? Inverse or proportional? Proportional. Charles' law states that at a constant pressure, the volume of a fixed amount of gas is directly proportional to the temperature of the gas. Mathematically, Charles' law is V equals kT, where V is the volume, K is a constant number, and T is the temperature in kelvins. You have to have the temperature in kelvins. Make sure you write that down and put a big star by it. Temperature has to be in kelvins. And then, of course, the actual equation, V1 over T1, so our original volume divided by our original temperature, equals our new volume, or our second volume, divided by our new temperature, or our second temperature. So again, they will give you 3 of these. You need to solve algebraically for the 4th. So let's go ahead and do a problem. Given known temperatures and a volume at a constant pressure, and obviously a constant amount, calculate an unknown volume. So a 2.0 liter balloon is at a temperature of 273 Kelvin. Okay, good. We're already in Kelvin. When the balloon is heated to 323 Kelvin, what is the volume at a constant pressure? All right, what are we solving for? So list everything and what we're solving for, including the unit of what we're solving for. So hit pause when you're done, hit play. Our original temperature, or our first temperature, is 273 Kelvin. Our second temperature is 323. Our first volume is 2.0 liters. We are solving for V2 in what unit? Liters. And let's stop and think. Our temperature increased. So our answer, is it going to be more or less than 2? If temperature increases, so does volume. So our answer is going to be more than 2. All right, so we have our volume and our temperature in Charles' equation. Go ahead and put the numbers in and solve algebraically, or solve algebraically and then put your numbers in. We're solving for V2. So we want the V2 by itself. We're going to multiply everything by T2 to move the 2 to the left. And then, of course, they put the V2 over here, so they just switch sides. And your answer is 2.37 liters. Okay, so we said it had to be more than 2. Is it more than 2? Yeah, not a lot, but it is more than 2. Our kelvins canceled. We're left with liters. Okay, looks like we did a good job. Joseph Louis Gay-Lussac investigated the relationship between gas, temperature, and pressure. Okay, so now we're doing temperature and pressure. Let's consider a cylinder or sphere that has a fixed constant volume and is filled with a fixed amount of gas molecules. At any given temperature, the gas molecules are moving because they have internal or kinetic energy. They collide with the walls and exert a pressure. Remember, pressure is force per area on the container. If you heat the container, the gas molecules receive more energy. If they have more energy, they're going to move faster. And the faster they're moving, they're going to collide with the walls more frequently and with more force. So the more force, the more pressure. Because the force of collisions increases and the volume and the surface area are fixed or stay the same, the pressure increases. By contrast, if you cool the container, the gas molecules lose energy. They're going slower. They collide against the walls less frequently and less force, so less pressure. All right, so if we look at the diagram, this one is set. See, we cannot move the piston. Our volume has to stay the same. So as we increase our temperature, our pressure does what? It increases as well, right? They are going faster. They're hitting more often and harder. Therefore, the pressure is also increasing. So as temperature goes up, so does the pressure. You're moving faster. They're hitting more often and faster at a faster rate. So they're going to be hitting with more force and therefore more pressure. So make sure you have your information written down for this slide. As temperature goes up, pressure goes up. Is that inverse or proportional? Proportional. And make sure you understand the why, okay? The why. So write that down too. Increased temperature equals increased kinetic energy equals faster, means more collisions, and the collisions are happening with more force. Look at the mathematics of Gay-Lussac's law. Gay-Lussac's law states that at constant volume, the pressure of a fixed amount of gas is directly proportional to the temperature of the gas. Mathematically, it is P equals KT. P is the pressure. K is the constant number. Again, we're not going to deal with those numbers yet, but it's a set number that's used all the time in this problem. And T is the temperature. Of course, we're going to be doing the more useful representation, which to me looks like party. That's how I remember this is Gay-Lussac, because I think, oh, it's two people, even though it's not. But two people, it's a party. So it's pressure and temperature. And we take our first pressure divided by our first temperature. That equals our second pressure divided by our second temperature. You can use this equation to calculate an unknown pressure when you are given known temperatures and pressure. You can use it to calculate an unknown temperature when you are given two known pressures and a temperature. So again, they're going to give you 3 out of 4. You have to algebraically solve for the fourth. And remember, as temperature increases, pressure increases. Okay, the problem in the K-12 lesson is not correct because they're not giving you the right stuff. So instead, we're going to do this one. So if a jar at 50 millimeters of mercury and 100 Celsius is cooled to 50 Celsius, what is the new pressure? And yep, I technically do need degrees Celsius, right? Degrees Celsius. There you go. All right, so go ahead and I'd like you to hit pause and solve this problem on your own. So the first thing I'm going to do is make a list of what I know. My first pressure is what? 50 millimeters of mercury. So we've used pascals. We've used kilopascals. This one gives us mercury. Do we have to change it? No, as long as our answer also has to be in what unit? Millimeters of mercury. Okay, so as long as they have the same unit, the beginning and end, it's fine. We don't care. All right, what's our first temperature? It is 100 degrees C. And our second one is what? 50 degrees C, except what is wrong? What is wrong? We need to have our temperature in what? Kelvin. So to change from Celsius to Kelvin, and I give you permission to add this part onto your cheat sheet for the gases, okay? So on the cheat sheet for the gases, I want you to write 273 plus degrees C equals Kelvin. All right, so add that to your cheat sheet so that you always have it. And I'm looking for my degree sign. There we go. There we go. So if our original temperature was 100 degrees Celsius, how many Kelvin would that be? I would simply take 100 plus 273, and it is 373 Kelvin. And what about now for our 50 degrees temperature? For our 50 degrees, 50 plus 273 equals 323 Kelvin. So make sure that you do those, and those are the values that we're going to use. So I'm going to underline them just to make sure we remember. Okay, so now we want to go ahead and get our equation. So we have pressure and temperature. It is a party. And so we have our original equation, and we are solving for P2. So I'm going to multiply everything by what? T2 to get the P by itself. So I'll have P1 T2 equals T1, or if you want to solve in and just cross multiply, that's fine too. Whatever you prefer, equals P2. And so I'm going to put in my numbers. I have 50 millimeters of mercury, and then that's going to be times my T2. So my T2 is 323 Kelvin, and I'm going to divide that by my original temperature, which was 373 Kelvin. And now I look and I see that my kelvins cancel off, so that's good. I'm only left with millimeters of mercury, so I set up my problem correctly. And now let's put that in our calculator. And we get 50 times 323 divided by 373. And we get 43.297. So let's round that to the nearest hundredth. Does the 7 make the 9 round up or stay the same? It rounds up, but in chemistry we're poor. We only add a penny. So instead of 29 cents, it would be 30 cents. So our answer would be 43.30 millimeters of mercury. Now let's check to make sure that makes sense. We have our temperature going down. So what should happen to our pressure? It should go down. Is our answer smaller than what we started with? Woohoo! That means we more than likely did it correctly. So review the gas laws. And again, make sure you have your cheat sheet printed off. Boyle's law states that at constant temperature, the volume of a fixed amount, same amount of gas, is inversely proportional or inversely related to the pressure of the gas. So when the pressure goes up, volume goes down. And there are the equations. Charles' law states that at constant pressure, the volume of a fixed amount of gas is directly proportional to the absolute temperature of the gas. So when the temperature increases, think of a piece of popcorn, what happens? Right? It gets bigger. The volume gets larger as well. And for Gay-Lussac's party equation, we know that we have to have constant volume, and the pressure of a fixed amount, so the same amount of gas, is directly proportional. So when the temperature goes up, so does the pressure. All right, that's what you have for this one. Make sure you can do all the problems before you take the quiz. There are problems on the quiz, and there are also some thought questions as well. And make sure you have your cheat sheet in front of you.